The nicest thing about this whole section is the actual maths and calculation. We are now going to talk about blackbody radiation and something called emissivity. Now, just to remind you, we have the electromagnetic spectrum, which starts with the smallest wavelength, gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. Here we have the smallest wavelength, but the highest frequency, all the way down to the lowest frequency and the largest wavelength. Okay, so that's just a little bit of recapping. Now, you know for a fact that a hot object, because you looked into radiation a few lessons ago, but any hot object will emit electromagnetic radiation in a wide range of frequencies. So this cup of coffee is emitting infrared. And you know that because when you touch it, it'll be hot. With time, the amount of infrared given off is much less because the temperature decreases. Now this is kind of the basic idea. The ideal blackbody, and this is a very heavy idea. It's at the root of quantum physics, but you do not need to know it at that level. You just need to think of it like this. A perfect blackbody, so if you can imagine this being perfectly black. What do we know about black objects? Well, from a couple of lessons ago, silver and white reflect, don't they? But black is a perfect emitter and absorber. Okay, in the case of a hot object, it will be emitting. Okay, so we're not considering the absorption properties, we're just considering the power to emit. So imagine this cup of coffee was in a jet black cup, and the coffee was jet black, and what it would do is, if heated, will emit all the wavelengths, right? All of them, gamma, X-ray, UV, violet, infrared, microwave and radio waves. Now that is the theory. Anytime in physics you see the word ideal, you know in practice it's not going to happen. In fact, what actually happens in this ideal blackbody, when you analyze the emissions, that means we get sensors to look at each of those traces. When analyzing emissions, what we find is not all the frequencies are immediately emitted with the same intensity. What? But surely they should be giving off everything. They don't. And this is a pattern that we see for all black bodies. In fact, for all hot objects, but we'll look at that in a minute. What we find is that not all the frequencies emitted will be equally intense. The spectrum of light emitted from a black body is shown below. Okay, so if we have a look at this graph, we're looking at, imagine this cup of coffee, this perfect black cup of coffee. We get some sensors and we look at the intensity. Now, I know it doesn't say exactly intensity, but just assume that this is proportional to it, against the wavelength for that cup of coffee. Let's imagine it's that green line. What we find is that it follows a kind of bell curve shape. Now, this is what happens to all hot objects. They don't just give off a whole range of wavelengths by the same amount. They peak. So this cup of coffee, and this is completely fictitious because I have no idea where the peak would be on a black cup of coffee, but this one is approximately in the infrared. Oh look, it does kind of fit, doesn't it? Because it's close to there. Although if this was our cup of coffee, it would be glowing red as well, which isn't happening. But anyway, every hot object has its own peak. The sun, for example, has its peak in this area here, right in the middle, and gives it a nice yellow orangey glow, which is why it's that colour, in fact. So what does this tell us? This tells us that every hot object gives off radiation in a non-linear way. It gives off radiation in a bell curve range of frequencies with a peak in one place. And what does this peak represent? The peak of this graph represents the most intense part of the spectrum. Again, you can see that here. It's this bit. And it's probably going to be the wavelength that's most prevalent. So if it's infrared, then it will be a hot object. If it's in the visible, it will be a nice bright object. If it's in the UV, then it will be something which is going to give you a tan. Okay. This is dependent. Let's finish off with this sentence, if I can. This is dependent on the temperature of the body. The hotter the object, the shorter the wavelength. Now, what does that mean? Well, let me tidy up the graph a second. What that means is, if you look at all these different curves, which are basically a different curve for a different temperature, and you can see the 3000 Kelvin has its peak somewhere in the infrared. You can see in the infrared. The 4000 Kelvin has it in the, well, it's kind of the red visible, and the 5000 Kelvin has it slap bang in the middle in the orangey yellows. Okay, so there is a kind of trend moving in this direction, which is shorter wavelength or higher frequency. Now that's probably a lot of information to take in, so let's see if we can sum it up. Okay, we have hot objects giving off light of different frequencies. What kind of frequency? What is the maximum frequency, or the most intense frequency that a hot object will give off? Well, it depends on its temperature, because each temperature has its own curve, and that curve has a peak of intensity in one of the wavelengths in the electromagnetic spectrum. The hotter it is, the closer the peak is to the smaller wavelengths. Does that make sense? Good. Because this can all be put into some kind of mathematical order. And the relationship that sums all this up looks a little bit scary, but it isn't. It's super easy to use and easy to remember. But of course, you don't need to remember it because it's going to be in your data booklet. But anyway, Wayne's displacement law tells you that the wavelength, the maximum wavelength, and what was that again? Well, if you find the peak, the wavelength which corresponds to that peak in intensity, okay, or wavelength max times the temperature will always equal this constant value, 2.9 times 10 to the minus 3 meters Kelvin. There's another relationship which will tell you a little bit more, but about the y-axis here, okay? The power relationship. You can see from the graph, and we'll read this out so it will make sense to you. You can see from the graph that as the temperature of the black body increases, the intensity also increases. Now, our first formula will tell you where the wavelength, or where it corresponds to the wavelength, but it doesn't tell you anything about that temperature's corresponding intensity. So what is this value on the y-axis? Well, that we can find from the Stefan-Boltzmann law. The Stefan-Boltzmann law relates the power emitted per unit area, intensity, is equal to the temperature of a black body. But of course, there's a constant. So the full relationship, which again you don't have to learn because it will be on the data booklet, is power is equal to sigma, where sigma equals 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the minus 4 times the area times the temperature to the power of 4. And temperature is always in Kelvin, remember. This is the Stefan-Boltzmann's constant at the surface of a body. Okay, so these are a little bit out of the blue formulas. There are lots and lots of little formulas to remember for this topic, but they are easy ones. They're not complicated when you apply them. And then the last thing that we need to talk about is something called emissivity. The Stefan-Boltzmann law, which we've just looked into, tells us what is the power radiated from a surface. However, not all objects, because we were talking about this perfect black body, but not all objects are perfect black bodies. In fact, No object is a perfect black body. But you can easily adapt for real use for any surface which does not behave like a perfect black body using the concept of emissivity. What is emissivity then? It's simply the power radiated by a surface, the real power, compared to the power radiated from a perfect black body of the same temperature and area. So we just need to add that little constant to our original Stefan Boltzmann's law. Normally, the power is equal to the sigma times the area times temperature 4. But we're going to scale it down. Emissivity gives us a factor which will reduce our value usually to include reality. So high emissivity, something which is very close to a black body, is going to have a high E value, and low emissivity would be something that's very reflective, because you imagine if your object's not even black at all, then this value, this theoretical value, needs to be scaled down. It's important to note that emissivity has to be between 0 and 1. A body with an emissivity of 1, so this frying pan might be a little bit close to it, represents a perfect black body, and something which is 0 is nothing like that. Somewhere in the middle, 0.5, represents an object which is only radiating 50% of the power of what a perfect black body would. I threw these numbers in randomly. This frying pan is not 1, and this frying pan is not 0. Somewhere close though.